আচ্ছা, তোমরা আমার কথা শুনতে পাচ্ছ?
তো এখন আমাকে
হ্যাঁ স্যার।
ইয়েস স্যার।
আচ্ছা, অহন কি জয়েন করেছো? অহন বোধহয় জয়েন করতে পারেনি এখনো।
না
না
স্যার
না
আছে
স্যার
তো।
ও আছে।
অহন আছো তো? ঠিক আছে, ঠিক আছে। আচ্ছা, সেকশন, হ্যাঁ ঠিক আছে, ঠিক আছে। আর সেকশন বি আছো এখানে? সেকশন বির কেউ আছো?
ইয়েস স্যার।
হ্যাঁ স্যার। হ্যাঁ স্যার
আচ্ছা
আছে
ঠিক
স্যার।
আছে, সেকশন বির
Yes,
সঙ্গে
sir.
তো আমার ইন্টারাকশন হয়নি এখন অবধি। ওই জন্য আমি চিন্তায় ছিলাম তোমাদের সঙ্গে যোগাযোগ সম্ভব হবে কিনা। ঠিক আছে, আমি আর শুভজিৎ বাবু কি আছেন? শুভজিৎ বাবু, আমাদের ল্যাবরেটরির শুভজিৎ বাবু কি আছেন? শুভজিৎ বাবু, আচ্ছা ধরো আমি শুভজিৎ বাবুকে একটু যোগাযোগ করে নিই আগে। শুভজিৎ বাবু কি আছেন? নেই বোধহয়, এখনো আসেননি, জয়েন করেননি। এ তেরিকা। আমার কথা শুনতে পাচ্ছ তোমরা? আজকে একটু বিভ্রাট হয়ে গেল, জানি না কেন। শুনতে পাচ্ছ আমার কথা?
হ্যাঁ
হ্যাঁ
স্যার
স্যার।
কিন্তু
হ্যাঁ
আপনার
ঠিক
আপনার
আছে,
যেটা
এবার শুরু
দেখাচ্ছে
করা
সেটা
যাক।
বড্ড ঝাপসা।
আচ্ছা, ঝাপসা লাগছে?
হ্যাঁ স্যার।
দাঁড়াও দেখছি কি করা যায়।
এইবার তাও একটু ঠিক।
এবার তাও একটু ঠিক না, দেখছি কি করা যায়। ঠিক আছে, আমি এই এ করে করে দেখাবো। Let's start our discussion. It's a very small discussion actually. You know that we cannot start our laboratory experiments practically. So it is just a simulation environment. Okay, and we want to demonstrate one particular lab study of the arsenal galvanometer. Actually, what we do in our laboratory that we will try to demonstrate. Okay, what I will do here, just I will explain the laboratory procedure first. And Shubhajit Babu is already in our line, in our link. He is there in the line. He and his team has in our laboratory has prepared one video. That video it will be shown to you by him, by Shubhajit Babu, and you will just when you see the video, you'll see how laboratory setups are looking like and how we can use them to demonstrate to conduct our experiment. So it will be a short video, a video of 1 minute. Let's start. Okay, again. So we'll demonstrate it, and Shubhajit Babu will show you the video and all these things. He is in the line already. He has prepared. He and his team has prepared this small video. Okay, for you. Okay. Now today's experiment, D'Arsonval galvanometer. Just the theoretical part only I'm showing you. You already have studied this galvanometer in the class. For section A, I have taken the class. For section B, some other teacher is, I think, has completed the discussion already. So in the circuit diagram, you will see actually there is a D'Arsonval galvanometer, and it is actually driven by one excitation, a 2-volt power supply. Okay, and in between this galvanometer and 2-volt power supply, there is a resistance R1, okay, whose value is shown here. It is shown that at 400 kilo. R1 equal to 400 kilo. Quite high resistance. And a key is there, K1, a switch. In parallel to the galvanometer, another resistance R2 is there, whose value, okay, is actually changing. We will reduce the value gradually, and the resistance is placed in series with the switch K2. Note that when the key is pressed, then only the resistance R2 will come in parallel, otherwise it will be only a series circuit with R1. Okay. Now you see in the procedure first, you will see the video later, but first you see what is the procedure, what you do. In run 1 actually, the switch K1 is closed and K2 is open. And then once K1 is closed for some time, the galvanometer,
দেখাবেন ক্যামেরা দেখা যাচ্ছে
this one. So you see when switch K1 is closed, when K1 is closed, we'll wait for some time and the galvanometer will attain a steady deflection. And that steady deflection will be noted. Now how the deflection is coming, you know there are two methods of getting steady deflection. One method is that there is a dial and pointer arrangement. When some current is flowing through a galvanometer, one option is just a dial will, the pointer will rotate, it will just move. There is another option is there that one mirror is placed in the former or near to the former of the galvanometer, and one light source is allowed to strike on the mirror, okay, allowed to be incident on the mirror, and the mirror will reflect the light beam, okay, and that reflected beam will come to the rotating spot, to the circular scale, and one illuminated spot, it will be visible on the circular scale. The scale is 1 meter away typically from the galvanometer. Means, say if there is a galvanometer, so note that, say if this is a galvanometer, one light source is just striking on the mirror and is reflected back. It is reflected back. Clear? And the reflected beam will just strike on the scale, circular
স্যার
scale.
অডিওটা শোনা যাচ্ছে না।
শোনা যাচ্ছে না অডিওটা, সে কি? Clear? Oh, then it is the bandwidth problem at your end. যারা শুনতে পাচ্ছ না, খুব সম্ভব তাদের নেটওয়ার্কে কোনো সমস্যা হচ্ছে।
হ্যাঁ স্যার এখন শুনতে পাচ্ছি, একটু তার মানে
এখন
প্রবলেম
পাচ্ছ?
হয়েছিল।
আচ্ছা আচ্ছা। So you see, the illuminated spot will be reflected back. It will strike on the circular scale. So from the position of the illuminated spot, you will come to know what is the steady deflection. Okay. And note that when our K1 is closed for some time, some current will flow through the galvanometer and the illuminated spot will attain some steady position. Okay. Now the thing is that when we, in the run 1, there is a second step, it is given here that the K1 in, so we note the steady deflection first, then in the next case what we'll do, we'll press the K1 just momentarily and we'll release the key. Once the key is released, K2 remains open for all the time. Okay, then there will be again some oscillation is there. So when there is a momentary closure of key, there will be some oscillation, and after the oscillation dies down, we'll get a steady deflection. Okay. Now, for after a momentary closure of switch K1, we'll note also what is the period of oscillation. How much it takes to complete one oscillation. The spot will go to the right, then left, and then will again come back to the right. So how much time it takes to complete the oscillation? That is the undamped period of oscillation. Okay. and we'll record this undone period of oscillation with a stopwatch. Okay, so that is the method. Then so in round one we do two things. First, we note the steady state deflection. Second, we note the undone period of oscillation of the galvanometer with the help of a stopwatch by connecting the key momentarily. Clear? Then next, in the round two, what we'll do, we'll vary the resistance R2. Okay, R2, its resistance will be gradually reduced. Then once its resistance is reduced, we will see that the oscillation will prevail always. But after some point of time, for a particular value of R2, we will see that there is no more oscillation found. It means the galvanometer is now no longer in underdamped condition. The galvanometer now will be critically damped, okay, or overdamped. You know, in critical damping or overdamping, there is no oscillation at all. So when we vary R2 and reduce the value, then what happens? Looking from the galvanometer end, the equivalent resistance is reduced, the coil circuit resistance is reduced. Clear? And you know that the electromagnetic damping is inversely proportional to the coil circuit resistance. Clear? So as the coil circuit resistance is reduced, the electromagnetic damping will increase. So from heavily underdamped condition, as we reduce R2, it will go towards the overdamped condition gradually. Our delta, the damping ratio, will increase. When it is exactly equal to 1, it will be critical damping. And when it is more than 1, it will be overdamping. Okay, but when we vary R2, it is expected that we will not reach to the exact value of critical damping for which delta is equal to 1. So there is a high chance that from underdamped we will go to overdamped condition, means no oscillation. Then once we get the overdamped condition, we will increase the value a little bit, value of R2 a little bit, so that we will notice at what point of time, at what particular value of R2 we get no oscillation for the first time. So when we get no oscillation for the first time, first value of R2, this value is corresponding to delta equal to 1. That is the critical damping. So that is the illustration. Now I want to give you one specimen table for the experiment, and then it will be clear to you. Now in round 1, say as I told you that we press the switch K1 momentarily and see what is the underdamped state, what is the oscillation, that will see it. So now in round 1, you see we note this period of oscillation for 10 full oscillation. Why 10 full oscillation? Because for one full oscillation the time is short, and there may have some error in recording the time, because there are personal error, human errors, all are there. So we just switch on our stopwatch and wait for 10 complete oscillation. So for 10 complete oscillation, you see we are recording the time. See, in one case it is 7.3 seconds. In another case it is 7.67. So we are completing 10 oscillation. Then for 10 oscillation it is 7.3 seconds. 7.3 seconds. So 7.3 by 10. So it is 0.73. So 0.73 is the time period. So we will do this step repeatedly. Why? Because we want to reduce our error, so we want to go for averaging. In one case we are getting 7.3 seconds for 10 oscillation. In another case, another 10 oscillation, it will take 7.67. Say for another 10 oscillation, another 6.9 seconds. So in every case we calculate what is the time for completing one complete oscillation, one oscillation, full oscillation. Then these are the time. Then we take the average of all such reading. So typically it is 0.73 seconds. Typically. So after averaging, we are getting it. So that is the time period. So, and we are taking minimum 6 readings. Okay, so 10 oscillation into 6. So we are taking it that way, and ultimately we are getting that particular mean time period. We call it, say, T0, capital T0. Okay, in round 1 we are getting it. Then what we do in the round 2, we want to reduce the value of R2. Okay. How to reduce the value of R2? Our starting value of R2 will be 5 kilo ohm. Our starting value of R2 will be just 5 kilo ohm. So that is 5 kilo ohm. Actually noted here, you see. So this is our 5 kilo ohm. Starting value of the resistance. From 5 kilo ohm, now we go on reducing this value. We go on reducing this value. How? So initially 5 kilo ohm, then we reduce it instead of 1 kilo. Actually, there is a resistance box actually, by means of which we can vary the resistance. Now in 5 kilo ohm, we note one deflection. Okay, when the value of R2 is 5 kilo ohm, we note the deflection is 175 in millimeter in the scale we are getting it. And we find that, okay, there is an oscillation. Okay, for 4 kilo ohm, we are getting in 171 millimeters. So, and the oscillation is found. We go on reducing the value. 5 from 5 kilo ohm, then 4, 3, 2, 1, this way, the oscillation is found. Now, for one value of R2, say here it is 350 ohm, as an example, we are getting one oscillation. We are getting no oscillation. No oscillation means we are not sure whether it is critically damped or over damped. Although it is written critically damped, but it may not be critically damped, it may be over damped. So from under damped, we are getting to over damped. So again, we are reducing it 340, 330. It will be not be Y, it will be always N actually, N. No. Once we get no oscillation for the first time, for all other values of resistances R2, thereafter, it will be always N. So these are all over damped conditions. But now we note what is the first value of R2 or highest value of R2 for which we get no oscillation. This value is either the critically damped condition or no, it's over damped condition close to critical damping. Then we will just come to a value which is in between 400 ohm and 350 ohm. Maybe at 357 ohm, I am just telling arbitrarily, maybe at a resistance of 357 ohm, we are getting for the first time no oscillation at all, no. Then that first value will be our critical damping. Okay, that first value will be our critical damping. So we have to note what is the first value of R2 or the highest value of R2 for which there is no damping at all. That value will correspond to the critical damping. So that value, so is the coil circuit resistance for critical damping. Once we know this thing, then we can find out many other galvanometer parameters. How? In the calculation, actually these things are there, that the angular steady state deflection theta s is found from the scale theta s. From this reading we can calculate, okay, L is actually 1 meter distance where the scale is placed. ds is the steady state deflection in millimeter. Then theta s will be our steady state deflection. From that we can get from that formula. Okay, our angular deflection of the spot when the critical damping is introduced. Okay, that calculation is also found, that under critical damping condition, what is the scale reading divided by L, and half of tan inverse this is corresponding to theta c. Okay, everything can be proved, but I am not going to the proof again here. Okay, and galvanometer resistance is also found from that particular reading. All things can be proved, but I am not going to the proof actually. And RC is the critical resistance in ohm, okay, used here. And other reading also we can find out easily, that undamped period of oscillation is actually 2 pi into root over A by C. You know root over C by A is actually the C, where A is the inertia constant and C is the control constant. It gives us the natural angular frequency. From that we can find out the time period. Now time period we can get it also from the experimental reading. So from that we can get the value of root over A by C. So T is found from the experiment. In the run 1 we get the value of T. In run 1 we get the value of T actually. This T I have calculated, that T average value. So once we know this T, okay, then from the theoretical result we will put that experimentally obtained value capital T, then we will find out the value of root over A by C. Okay, and the current flowing in the galvanometer also can be found by the applied voltage by the circuit resistance R1. It is a steady state current that is flowing through there. And we can find out the current sensitivity also. You already know this thing, that is the steady state deflection by this particular current. Okay. And the control constant also can be found from that reading. So all the constant, the galvanometer constant or meter constant, it also can be found. All the things can be proved easily, but I am not going to the proof. Then damping constant is also can be found. B is following that relation, and inertia constant is given by these, A equal to that. So ultimately we can get all these things, but better that we see the video first. So I'll request Shubhajit Babu to run the video. Okay. So Shubhajit Babu, please run your video. Because of some problem, Shubhajit Babu may not be able to talk. It is a problem at his system, but he will run the video. Okay. So we are waiting it. Yes. Shubhajit Babu is sharing the screen now. Please see, you will get it.
Today we are going to perform the study of D'Arsonval galvanometer. You can see here is the setup for such experiment. This is the circuit diagram. You can see two resistances are there, R1 and R2, where R1 is a fixed resistance and R2 is a variable resistance. And two switches are there, K1 and K2, and obviously there is a galvanometer, D'Arsonval galvanometer, you can see, and 2 volt.
Sir, the video isn't visible.
আনপিন কর হয়ে যাবে।
ভিডিওটা তুমি এখানে একটা অপশন আছে, ওখানে ক্লিক করো, পেয়ে যাবে।
This
Google
one
Meet এর
is
নিচের দিকে
R1.
দেখো।
This is the decade resistance box. We are using it as a SR1, which is a fixed resistance. This one is R2, a variable resistance. This is also a resistance decade box. Okay, next, this is a DC power supply, 12 volt DC power supply, and this is the galvanometer element. Okay, you can see here is the light source. From here, a light beam is going to 2 volt DC power supply, and this is the galvanometer element. Okay, you can see here is the light source. From here, a light beam is going to that galvanometer, a mirror is there, okay, and it is reflecting back to the scale. Here, a spot, light spot. Okay, this is the indicator of the galvanometer, and when we will perform the experiment, you can see that the light spot is reflecting. And this is a centimeter scale. From here we will get the reading. Later when we will perform the experiment, then you can understand actually how it is working. And this one is K1 switch and this is K2 switch. Okay, by putting this, we will close the switch, and by removing this, we will open the connection of the switch. And this is a stopwatch. We will use it to measure the oscillation period. R1, as you know, R1 is a fixed resistance, and we will fix the resistance value to 400 kilo. Throughout the experiment, that value will not be changed. Now we will perform our experiment. Now run one. First, press the key K1 with key K2 open and note the steady deflection of the galvanometer spot. Let it come to its steady position. Now it is stopped. I think a little bit deflection is there. Okay. Now we are going to note the undamped period of oscillation by momentarily pressing and releasing the key K1. Just check. Now you see that this spot is oscillating. Now we are going to count this oscillation for 10 times. At the same time, we will start the stopwatch to take the 10 undamped oscillation time period to find out the undamped oscillation time period. In run 1, we found the steady deflection of galvanometer and the undamped period of oscillation. Now we will move to run 2. In run 2, first of all, we are going to set the value of R2 to 5 kilo ohm. Okay. You can see now gradually we are going to decrease the value of R2 and check the deflection of the galvanometer, and we will check whether it is in underdamped condition or in overdamped condition or critically damped condition. So by this process, we will get the value of R2 in which the galvanometer is critically damped. Now, when the value of R2 is 5 kilo ohm, we will start to check whether it is in underdamped condition or in overdamped condition or in critically damped condition. So first reading we will take at 5 kilo ohm. You can see that we just put the K1 close when K2 also is in close condition. Now you can see when we put the K1 key in close condition, this is an underdamped condition. Okay, and you have to take the value also from the scale. By varying shunt resistance R2 from
স্যার
equal to
সাউন্ডটা
1
ক্লিয়ার
kilo in
শোনা
steps
যাচ্ছে
of
না
1 kilo and then in steps of 100 ohm or as per the requirement. By this process, now we came to the value of 1 kilo ohm of R2. Now you can see, okay, now you can see the value, actual value has been decreased, but still it is in underdamped condition. So in 1K, you saw that the value has been decreased, but still it is in underdamped condition. So now we are going to change the value of R2 in steps of 100 ohm. By changing this process, we came to the value of 400 ohm. Okay, now we'll check it in 400 ohm. Yes, yes, the value, you can see that value again value has been decreased, but still there is still it is in underdamped condition. You can check it again, this show. Yes, it is still in underdamped condition. Now we are going to the value, next value, that is 300 ohm. Change it to 300 ohm. Yes, 300 ohm. Now we will check whether it is in underdamped condition or not. Yes, you can see it is now in overdamped condition. Yeah, okay. So in 400 ohm, it was in underdamped condition, and in 300 ohm, it is in overdamped condition. So now we know that the critically damped point is in between 400 ohm and 300 ohm. So to get the critically damped point, now we are going to decrease the value of R2 in steps of 10 ohm from 400 ohm. Okay. Now by this process, now we reach to the resistance value of R2 is 340 ohm. Now we will check in 340 ohm whatever result we will get. Okay. Again, please do it again. Yes, I think we got the critically damped point. Okay, you can see there is no oscillation, directly it is coming to the point and stop. Okay, so now I can say the galvanometer becomes critically damped. And remember, don't forget to take the value for each reading. Okay.
Thank you. Thank you, Shubhajit Babu, for your video. I think there is some problem in the audio quality. তোমাদের কি মনে হচ্ছিল অডিওটা শুনতে পাচ্ছিলে ভালো করে?
না স্যার, কেটে কেটে যাচ্ছিল খুব।
হ্যাঁ হ্যাঁ, আমিও
অডিও ভিডিও
এটা আসলে ওই যদি সবারই এটা আমাদের প্রবলেম হয় তাহলে বুঝতে হবে যে হয়তো ওই ট্রান্সমিটিং এন্ড থেকে হতে পারে। যাই হোক, এটা কিছু করার নেই, এমনি গুগল মিটার থেকে। কিন্তু জুমে আবার ওই 100 জন এক্সিট করে গেলে করা যায় না। গুগল মিটের তার একটা উপায় আবার আছে জানো, সেই জন্য আমি
এখানেও
গুগল
তো
মিটে
নেই
বাধ্য হলাম।
100 জনের
হ্যাঁ
উপায়টা।
হ্যাঁ,
না তো 100 জনের বেশি ক্লাস করা যায় না।
কি গুগল মিটে ওই ইউটিউব চ্যানেল করে আর কি, লাইভ ইউটিউব চ্যানেল করে তখন সেটা বাকি জন সেটাতে দেখতে পাবে আর কি। কিন্তু জুমে
স্যার
অনেক
জুমেও
ক্ল্যারিটি
লাইভ
ভালো।
স্ট্রিম
আমি
করা যায়।
পার্সোনালি জুম খুব প্রেফার করি। হ্যাঁ বলো
স্যার
স্যার এই
জুমেও লাইভ স্ট্রিম
ভিডিওটার
করা যায়
ড্রাইভ
ইউটিউবে।
হ্যাঁ বলো, দুজন একসাথে
স্যার
কথা
এই
বলছিল তো বলে। হ্যাঁ
হ্যাঁ স্যার, এই ভিডিওটা ড্রাইভ লিংকে যদি একবার আমাদের সাথে শেয়ার করেন তাহলে ভালো হতো, ড্রাইভে আপলোড করে
ও
আমাদের
আচ্ছা
দুটো
আচ্ছা,
সেকশনে।
শোনো এই ভিডিওটা যেটা ব্যাপার সেটা হচ্ছে যে এটা আরেকটু মডিফিকেশন হবে আর কি। ঠিক আছে, এটা আরেকটু
আচ্ছা ঠিক আছে।
মডিফিকেশন হবে, হয়ে টয়ে দেখা যাক। আর ইন দ্য মিন টাইম যদি আমরা ল্যাব তোমাদের করিয়ে দিতে পারি অল্প অল্প করে করে পরে আর কি কিছুদিন পরে, দ্যাট ইজ মানে দ্য বেস্ট থিং আর কি। আমরা দেখবো কি করা যায় আর কি, সুতরাং একটু ওয়েট করো, আগে দেখি কি দাঁড়ায় ব্যাপারটা আর কি। এমনি তোমরা এক্সপেরিমেন্ট গুলো এখন জাস্ট মোটামুটি বুঝে রাখো, যে অন্তত এটা শোনার পরে এইটুকু জানলে যে এরকম একটা এক্সপেরিমেন্ট হয় এবং মোটামুটি এইভাবে করে জিনিসগুলোকে এরকম এরকম দেখতে, হ্যাঁ মোটামুটি এরকম একটা ওভারঅল একটা ধারণা তৈরি হলো। এইটুকুই আমাদের উদ্দেশ্য। খুব বিরাট কিছু আমরা করে ফেলতে পারবো এমনটা এক্সপেক্ট করো না আর কি। এখন ভবিষ্যতে দেখা যাক, আমরা চেষ্টা করব যদি তোমাদের এটা করিয়ে দিতে পারি আর কি, পরে অল্প অল্প করে ডেকে 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 ডিপার্টমেন্টে আর কি। এমনি রিগার্ডিং দিস এক্সপেরিমেন্ট যদি কোনো কোয়ারি থাকে বলো, আমরা দেখছি ট্রাই করে, নাহলে শেষ করে দেবো এখানে আর কি। জাস্ট ধারণা দেওয়াটাই এখানে উদ্দেশ্য ছিল, খুব বেশি কিছু করানো এইভাবে তো বুঝতেই পারছো, ল্যাব আর কি করে করাবো এইভাবে, থিওরি ক্লাস হলে একরকম ব্যাপার। এনি কোয়ারি নেই বোধহয়? ঠিক আছে, তাহলে আমরা আজকে শেষ করছি। পরে কোয়ারি হলে আমায় জানিও, দেখবো এখন কি করে যায়। হ্যাঁ বলো। হ্যাঁ হ্যাঁ, ও কি অহন বলছো? ও তোমার কাছে রাখো, আমি পরে তোমার সঙ্গে কথা বলে নেবো। সবকিছু তোমার সঙ্গে রাখো এখন। অহনই হচ্ছে আমার ভরসা, আমি যা দেখছি আর কি। অহনের উপর অনেক দায়িত্ব দিয়ে আমি মোটামুটি নিশ্চিন্ত আছি। ঠিক আছে, পুষ্পলও অবশ্য কখনো কখনো আমাকে করেছে, হেল্প করেছে। যাই হোক, ঠিক আছে, অহনের কাছে রেখে দাও, আমি পরে তোমার কাছ থেকে কথা বলে নিয়ে নেবো যা করার দরকার। ঠিক আছে, থ্যাংক ইউ, থ্যাংক ইউ, ওকে।
ইউ আর লেট ম্যান।
অলরেডি 99 থেকে 82 হয়ে গেছে।
এরম কথা আগে বলতে হয়।
হ্যাঁ, স্যারের সময়
ভাই,
দিতে পারিস তো?
আরে ভাই, এর ভরসা তুই এসব করলে হবে?
আরে না, তুই স্যার থাকলেই বলতে পারতিস, স্যার তোকে ভরসা করে, স্যারের সঙ্গে তুই
হুম।
চালাচালি করিস।
ও ওপি।
এ অহনের কি প্রশংসা শুনলি?
হ্যাঁ,
সবাইকে প্রেজেন্ট দিয়েছে।
তুমি এবার মাইলেজ পেতে যাই, মাইলেজ পেতে এখন।
পুষ্পল জ্বলছে, পুষ্পল জ্বলছে।
পুষ্পলকেও বলেছে তো,
হ্যাঁ,
ওর জ্বলার কিছু
mileage পেলো, ওই জন্য তো অন হলো।
আরে আমারটা তো কনসোলেশন প্রাইজ, ওকে তো একদম বুকে তুলে নিয়েছে স্যার।
ওই স্ক্রিনশট নিবি
একদম।
নিয়ে তাড়াতাড়ি
আবার আবার
অহন ওপি ইন দ্য চ্যাট।
বসে আছে বক করে যাচ্ছে।
জয় জয়
এটা-
অহন
হ্যাঁ।
অহন বিজেপি
হুম?
জয়
লিভ করলাম তাহলে।
স্বর্ণদ্বীপ আর কি, ওফ আলাদা।
কিছুই না, আগের দিন ক্লাস নিয়ে একটু হ্যাঁ
কাছের লোক, কাছের লোক, কাছের
হ্যাঁ।
লোক।
আরে আমার বাবা হলো
এটা?
এসআর এর একদম হার্টে একটা কি বলবো খুব স্পেশাল স্থান আছে।
জয়ত হচ্ছে এসআর স্যারের ডিসি মেশিন।
মানে
এটা কি ছিল ভাই?
হ্যাঁ মানে
ও আচ্ছা, এই ব্যাপার। না না, ইনস্টার গল্প পাবলিকে কেন ভাই? ওটা থাক, ওটা ওকে মাঝে মাঝে একটু ইয়ে করবি, ব্ল্যাকমেল করবি। হ্যাঁ, ব্ল্যাকমেল করবি।
ইনস্টার কি বলবো আমি বুঝতে পারছি না তো।